Hi, this is Chirag Gupta, and I'm going to be presenting my recent paper on calibrated prediction. This is joint work with Alexander Podkupayev and my advisor Aditya Ramdas. As promised in the title, we study three notions of uncertainty quantification. And this is the usual classification setup. You have covariates X, labels Y that belong to this set, a predictor F, and some tolerance alpha, which is usually a small number between like 0.05 or zero point 0.1. And this paper focuses on binary classification for most of the paper, which is the setting where y is either 0 or 1, and the range of f is 0, comma 1. So it's and a number in the interval 0, comma 1. Calibration for a predictor f is defined as the property that expected value of y given fx is equal to fx. So in the binary case, this leads to probability of y equal to 1 given fx equal to fx. And here you can think of as trying to predict the probability of rain on a particular day. And if predictor says, say 0.7, then you want it to actually rain with probability 0.7. So that would be called a well-calibrated predictor. Another notion of uncertainty quantification is prediction sets. So prediction sets essentially allow you to make more than just a single prediction of 0 or 1, but they allow you to predict the set 0, comma 1 if you're not sure about the prediction. And while we are allowed to predict an entire set, like the goal is that the accuracy should be guaranteed to have a lower bound. So that means that the probability of y belonging to this set that you predict should be at least 1 minus alpha. A confidence interval is a function c that attempts to cover the expected value of y given fx. So naturally, you can think of this as related to calibration. So a confidence interval would say that it will rain with probability between 0.6 and 0.8. And again, you want that the expected value of y given fx should belong to this confidence interval with probability at least 1 minus alpha. So this intuition between calibration and confidence intervals is one of the things that we will capture in this presentation and in our paper. To do that, the first thing we need to do is define an achievable notion of calibration. So notice that this current notion, probability of y equal to 1 given fx equal to fx, is not achievable in finite samples because you cannot like estimate the exact probability of y equal to 1. So we want something approximate, and this is a natural approximate definition that we formulate. And this says that these two values should be epsilon closed with probability at most 1 minus alpha. To relate confidence sets and prediction sets, confidence intervals and prediction sets to calibration, we consider them with respect to a particular function f. So calibration is always with respect to a function f, and hence we consider a prediction set where we are interested in the probability of y belong to s of f of x. So instead of sx, we have s of f of x. And similarly for confidence sets. So the intuition is that instead of giving something for every x, we are allowed to merge some of the x's together and give some, but be valid with respect to fx instead of just x. Okay, so having set up these three definitions, we now come to the main sort of diagram of the paper, which is this diagram on the left. So here we are relating these three notions for distribution-free binary classification, which is the focus. So distribution-free means that we're interested in uncertainty quantification without making any distribution assumptions. So it's some sort of provable distribution-free setting. And so what we show, as I'll discuss in the rest of the talk, is this diagram, and I'll go through each particular connection. But the final goal that these relationships lead to is an impossibility result for distribution-free calibration for specific kinds of f, which I'll describe. So let's first consider calibration and CI. So I briefly mentioned this on the definition section, but basically we show this formally. So this is how it's done. So consider that you have calibration, which is the definition is given here. Then you can define C as Cfx equal to fx plus minus epsilon. And it's easy to see that this construction guarantees that expected value of y given fx belongs to Cfx with probability at least 1 minus alpha. On the other hand, suppose you have this, which is confidence intervals with respect to f. then you can define mx as the midpoint of cfx and r as the largest radius of all the intervals cfx. And you can prove this calibration guarantee. And this is a calibration guarantee because you can think of f as m and epsilon as r. And it can be shown that this guarantee holds. Next, we consider the connection between distribution-free confidence intervals and prediction set. So one thing I forgot to mention is that the connection between CIs and approximate calibration is general. It does not depend on a specific F or the distribution-free setting. However, the connection between confidence intervals and prediction sets depend on the fact that we're in the distribution-free setting with a specific kinds of F, as I'll describe now. The proof for this goes via a construction of a new distribution Q. So suppose the data generating distribution is P, we'll now construct a new distribution Q. And this distribution Q is motivated by construction in Wolf et al., which is their book Algorithmic Learning in a Random World, and the recent preprint by Rina Barber. The basic goal here is that this distribution Q is somewhat non-smooth and it's very hard to fit it, but it's still indistinguishable from P. So, okay, let's go through the construction and then things will become more clear. So the first thing is that the marginal distribution over X is the same for both Q and P. However, for the conditional distribution of Y given Fx, this is how we describe it. So first, consider any Z in the range of F and define this random variable R of Z that is sampled as Bernoulli with the bias expected value of Y given Fx equal to Z. And this is the expected value of Y given Fx under P. So I sample R, and once I have sampled R, I define the distribution of Y given Fx as simply R of Fx. So basically Q is now no longer a distribution, it's a fixed value which is given by R of X. So it's deterministic given R. So Q given a value of Fx is just either 0 or 1 deterministically. And hence the next statement can be written for Q, which is that the expected value of Y given Fx is actually equal to Y given Fx deterministically. And hence confidence intervals and prediction sets for Q are exactly the same. However, it can be shown that Q is in fact indistinguishable from P if P Fx is non-atomic, which means that P Fx does not contain any atoms. And this leads to confidence intervals giving prediction sets also for P. Since for Q, they're exactly the same and it's indistinguishable, you must also get it for P. So I have a couple of examples here of distributions that are non-atomic and atomic on PFX, but I won't go through this. You can pause and have a look at them if you're interested. Finally, the goal that we achieve through these connections is the following. So basically calibration or confidence intervals aim to cover the expected value of Y given Fx. However, prediction sets aim to cover the true label Y itself. And thus we expect the length or the width of prediction sets to be larger than that of confidence intervals. In particular, suppose Y given X is Bernoulli 0.5, which is just a coin flip for every X. Then it can be shown that valid prediction sets have width at least 0.5 minus alpha. And thus, by this relationship, the valid confidence intervals should also have this width. However, we know that ideally the confidence intervals as the number of data points tend to infinity should just be a small interval around 0.5. And what this lower bound shows is that even if the number of data points tend to infinity, we don't have this lower bound. And by this connection, this also leads to a lower bound for calibration, essentially saying that your calibrated intervals cannot shrink to 0 as the number of data points tend to infinity. And so what this means is that for the specific kinds of F for which this connection holds, distribution-free calibration is impossible. So this is the main theorem of the paper. However, this is for a specific kind of F. So the next thing that we have is, well, for what f is it possible to get distribution free calibration? And these f's are not the typical f's that we consider for calibration, such as Planck scaling or beta scaling or temperature scaling. However, a property, this property is satisfied by the algorithm called binning, which is a simple algorithm. It's a post hoc calibration scheme of a given predictor G. So you have a predictor G and you're going to calibrate it. So we consider any partition of 0, comma 1 in the interval in intervals I1, I2 to IB, and these are disjoint and exhaustive intervals. Now we take some calibration data which is drawn independently of G, and we take these points and throw them into the B bins. And for every bin, we define the following entities for the calibration guarantee. So S hat B is the number of points in bin B, and pi hat B is the empirical mean of the Y values in bin B. And pi B is the thing that we're trying to estimate, which is the expected value of Y given Gx. And we can show that binning provides distribution-free calibration. Specifically with probability 1 minus alpha, for every bin B, we can show that the difference between the expected mean and the true, the empirical mean and the true mean is at most square root ln B over alpha over S hat B. Now, S hat B, recall, is the number of points in the bin B. And this may be unsatisfactory because you don't know how many points there are, but we can use this uniform mass binning scheme of Kumar et al. To actually show that S hat B is omega n over B, and this is the final guarantee that we can show. Finally, binning is can be easily extended to many more settings, and we discussed two settings, which is streaming data and covariate shift in our paper. So yeah, I hope you're interested in our work, and you can check out our poster and the paper at the following link. And we'd love to see you at the discussion session. Thanks a lot.